Okay, so this time we're going to do another simple problem. I like this because this looks a lot of focus. Here's another design type of problem. It's a simple problem to figure out the stress analysis part of it, but it introduces a couple of concepts that you might not have seen before: factor, safety, and then the concept of yield stress. Okay? And we'll talk about it from a design standpoint. So this is problem F1-19, page 54 in Hibbeler. A 30 kilonewton force is applied onto this eyelet. The problem is saying that we're interested in looking at designing the diameter for the shank of this eyelet. It's given by the diameter lowercase d. It's made out of a material that has a yield strength of 250 megapascals. So that means once the stress in this material exceeds 250 megapascals, it starts to behave plastically and stretches such that when you unload it, the deformation isn't recovered. We'll talk more about that in the next chapter. All right, but it's saying basically you want to have the stress not exceed that. Well, not only does it want you to have the stress not exceed that, it's specifying an additional factor of safety of 1.5 against yielding. All right. So what this is typically, in reality, you don't know fully these boundary conditions. There might be some dynamics. There might be some other misalignments or geometrical errors that might happen. You're designing sort of the ideal situation, and so they want an additional 50% factor of safety here. So the way the factor of safety goes is the factor of safety is defined as the allowable stress, or in this case, the theoretically maximal stress, the yield stress in this case, because we're designing to yield. You can also do factor of safety to failure, and then it would be the failure strength, which would be more. Okay, but this is the yield stress they're talking about we're designing to, over the maximum allowable. This is what you're calculating. Okay, so this is actually the max stress that we can permit in our design. So this is actually the max stress. Equals the yield over the factor of safety. And in this case, that's 250 megapascals over the factor of safety of 1.5. Then that gives us 166.7 megapascals. So that means the maximum average normal stress in that cross-section of that shank cannot exceed 166.7 megapascals. Or in fact, that's what we're going to design to. All right? Okay. So this factor of safety drops the stress down. And you don't have to worry. I mean, I don't memorize this equation, but obviously the factor of safety is such that it should drop the stress. So in this case, you know, if you screw it up, you'll find out that your design stress is greater than your yield. And obviously that's not correct. You multiplied when you should have divided or something like that. All right. So again, it's this concept you should understand. Okay, factor of safety takes into account sort of some of these other intangibles that might actually happen that you haven't accounted for. It gives you a little margin of error. Okay. The other way you can use factor of safety, right, is you know the yield, you have a design, you can figure out the max stress, and then you can sort of back calculate a factor of safety. Hopefully your factor of safety is greater than 1. Okay. All right. So here, let's do the problem. So basically, if we do a free body diagram like follows, here's the eye. And we're applying on here the force of 30 kilonewtons. This has a diameter of d, right? We have a equal and opposite normal normal reaction force, internal reaction force. So in this case, you can do sum of forces, and you find out that N has to equal, obviously, 30 kilonewtons. All right? Now that gives me, I can use that to compute the average normal stress. That's the N over the cross-sectional area that the stress is being applied to. That's this one, which is pi on 4 d squared. So that gives me the stress is N 4N over pi d squared. All right. Now I know this is the 166.7. I want to find this, so I can solve for d. That's the square root of 4n, I guess I could take the 4 out, over pi. This is the max, right? This is the max allowable, right? So that is 4 times 30 kilonewtons over pi times 166.7 megapascals. We got to be careful of our dimensionality of the units. So the easy way to do this is always to just, I kind of, instead of the K, let's put in 10 to the third. So now this is newtons, 4.3 times 10 to the third newtons. And then here for the mega, we can put in 10 to the sixth. And now this cancels with this, making that a 3, or to the minus third. So now I've got square root 4 times 30 newtons over pi 166.7 times 10 to the third, and that's pascals, which is newtons per meter squared. These guys cancel out, and you'll see you'll get a fundamental units here of meters. Okay? Now we can change that to millimeters later on. Let's just do the math. So this is 4, enter, 30 times. It's 120. 6 divide 166.7 3 divide, and now we take the square root, and so that gives me d equals 1.51 times 10 to the minus second meters, and that would be 15.1 millimeters. Okay, so that's the answer. 15.1 millimeters should be the diameter. Okay.